Hello everyone, and welcome back. Today we're going to be continuing our exploration of real-valued sequences and focus on the concept of subsequences. So what exactly is a subsequence? So as usual, we're going to be beginning with a sequence in the set of real numbers, and again, the domain of a sequence is the set of natural numbers. And let's list out the values of this sequence to be A1, A2 down to AN, and so on. And then what we're going to do is we're going to define a sequence of natural numbers, and this natural number sequence must be increasing. In particular, nj must be less than nj plus 1 for j greater than or equal to 1. So we can view the set M as a set of increasing indices. A set of increasing indices. Okay, so what are we going to do with this set of increasing indices, right? And keep in mind, n1, n2, nk does not need to be 1, 2, 3, 4. It could be 1, 5, 10, 11, 15, 28, 32, and so on. As long as it's a subset of the natural numbers and it's increasing, it satisfies as a set of increasing indices. So what are we going to do with them? Well, we're going to create a subset of that set of real numbers A, and we're going to call that set B, and it's going to be elements in the sequence of A, but indexed with respect to that indexing set M, right? So here, N1 is an index, N2 is an index, Nk is an index, and so on. So all of these elements, A subscript J, are elements in the sequence A, but not necessarily all of them, just a subset of them. And we call B, the sequence of real numbers, a subsequence of the larger sequence A. So let's see if we can break that down into a couple examples. So let's look at a nice little set A. Now let's assume it has the values A1, A2, A3, and so on. And as usual, we're going to assume that they're all real numbers. So let's define the set B to be equal to A1, A3, A5, A7, and so on. So all of the odd indexed values of A, right? So is B a subsequence of A? Well, we have 1, 3, 5, 7, and that's an increasing sequence. So this is a subsequence of A, right? So that matches. So what would be an example of a subset of A that is not a subsequence of A? So for example, we could do A2, A1, A4, A3, A6, A5, and so on. So if we don't really consider the order of the set, A and C appear to be the same set, but the order for which they're presented is not in increasing order with respect to their indices, because we know 2 is less than 1, 4 is less than 3, and so on. So therefore, this is not a subsequence of A, right? Even though it does contain a subset of the terms, the presentation and the order of those terms must be preserved, right? So that's a requirement. So let's look at a very important sequence, and let's look at a couple sequences. Let's define A to be equal to the sequence -1 to the power of n, and n to be equal to the set of natural numbers. And if we list these terms out, what we're going to have is we're going to start off with -1, +1, -1, +1, -1, +1, and so on. So what are we going to do? So let's grab, or see if we can grab some of these terms. For example, let's see if we can grab the terms that only have 1 in it. So that's here, A1, A2, A3, A4, A5, A6. So all the even indices are the ones that contain 1 only. So what we're going to do is we're going to define B to be equal to the terms A2k, where k is a natural number. So that's going to be A2 times 1, 2 times 2, 2 times 3, 2 times 4, which is going to be A2, A4, A6. And here, obviously, A2k must be an element of the sequence A, right? So if we sort of list these values out, so B is going to be equal to A2, A4, A6, A8, and so on, which if we list those values out explicitly is going to be 1, 1, 1, 1, and so on. So is this a subsequence of A? Yes, indeed it is. So this is a subsequence of that alternating sequence -1 to the m. Right? So that's pretty much what a subsequence is. So the first theorem that I want to investigate that is associated to subsequences of real-valued sequences is the following. So what we're going to do is we're going to be starting off with a sequence in the set of real numbers, and we're going to be assuming that this sequence converges, right? So we get several different things from that. For example, if it's convergent, we also have that that sequence is bounded. And also let's assume that we have a subsequence of that convergent sequence, right? So if we say that this bigger sequence converges to, say, alpha, what can you say about any subsequence of that convergent sequence? Well, this theorem claims that the limit of any subsequence of a convergent sequence is the same exact limit of the overarching sequence, in this case, alpha. So how are we going to go about justifying this, right? So if you have a sequence that converges, any subsequence of that convergent sequence also converges to the same exact limit, right? So how are we going to prove? So what we're going to do, as usual, we're going to assume epsilon is greater than 0. So by the convergence of real-valued sequences, that means there exists a natural number, n, such that if little n is bigger than bn, then for all n bigger than big N, then an minus alpha is going to be less than epsilon. So that's what we mean by an converges to alpha. So let's pick our subsequence, right? Because since we have a real-valued set, we can always choose a subset of it, right? So let us assume that a and k, where k ranges from 1 to infinity, so nk is our increasing sequence of indices. Let's assume that this is a subsequence of our convergent sequence an, right? So what do we know about those indices n1, n2, n3, and n4? So since n1 is less than n2 is less than n3, that's going to be less than nk, and that's going to be continuing onward, is an increasing subset of the set of natural numbers, that means that nk will always be bigger than or equal to the value k in that index, right? So the index of the index, right? So the index of our subsequence is always greater than or equal to the index of our original sequence, right? And you can list out a sequence and a subsequence and verify that this is always the case. You could also do mathematical induction if you're not quickly convinced of that. So if that is the case, that means if k is bigger than or equal to capital N, that means little nk will be greater than or equal to capital N, right? So if that is the case, that means a nk minus alpha will be less than epsilon, if that is true, and then that would imply that the limit of our subsequence a and k will also be equal to alpha, right? So pretty much what we have here is if we have that our sequence and the limit value are arbitrarily close to each other, then any sequence and the limit of the overarching sequence will also be arbitrarily close to one another. So that's practically what this proof is built upon, right? And that's the proof of that. Okay, so let's actually do a quick numerical example to sort of illustrate how this can be used, right? So let's give a sequence here and a claim for its limit. So let's assume that somebody gives you the limit of x to the power 1 over n, where x is a number that is strictly bigger than 1, 1.2, 1.3, 2 pi e, and so on. So what do you think the limit of this sequence is? So it's x to the power of 1 over infinity, practically, right? So what is that going to be? So if x is bigger than 1, well, 1 over infinity practically goes to 0, and x to the power of 0 is going to be 1. So some people will claim that this is equal to 1. Well, is this indeed true? Well, we'll find out in a moment, won't we? Right? So let's see if we can prove or disprove this statement. So we're going to be letting our sequence an be equal to x to the power 1 over n. So x is to the power 1 over n. And since x is assumed to be bigger than 1, then what do we have? So that means x to the power of 1 over n, which is equivalent to the nth root of x, will also be bigger than 1. And that's properties of radicals because this radical function, nth root, is a monotonically increasing sequence. And that's obviously going to be true for any n instead of natural numbers. And again, if you're not convinced of that, then you can use mathematical induction on the index of that radical in order to justify that. Right? So notice here we have our sequence an, and it's always greater than 1 for all n. So that means what is true about the sequence an? Well, that means an is bounded below, and particularly by 1. Okay, so that's pretty useful. So let's just put that aside just for a moment. Also, if we look at 1 over m plus 1 and 1 over n, since n is a natural number, we know that 1 over m plus 1 is going to be less than 1 over m. So from this identity, what can we get from that? Well, that implies that x to the power of 1 over m plus 1 will also be less than x to the power of 1 over n. And again, that's another real number property that you can use or prove via mathematical induction. And obviously this and this are sequences, just at different indices. So that means that am plus 1 will be less than an. And as usual, that's true for all n in the set of natural numbers. So what exactly does this mean? Well, that means that an is a decreasing sequence. Right? So what do we have so far? So we have that an is bounded below, and an is a decreasing sequence. So what does that mean about this sequence am? So by the monotone convergence theorem, that means that the limit of the sequence am, which I'm going to call L, exists and is in the set of real numbers. Okay, so what can we use this for? So now we know that the limit exists. Now let's play around with that theorem about subsequences, and any subsequence also having the same exact limit, right? Because if this sequence converges, any subsequence of it also is going to converge to the same value. So the limit of an will be equal to the limit of a to n, the even indexed subset of am. And that is going to be equal to the limit of x to the power, not 1 over n, but 1 over 2n, right? So those are the even terms. And we know that by definition, that's going to be equal to the square root, by properties of limits, the limit of x to the 1 over n, or 2n as well. Right? And that's going to be equal to, so again, where is that coming from? So that 1/2 is giving us that square root, and the x to the 1 over n is practically what's going on there, right? Because keep in mind, x to the 1 over 2n is the same as x to the 1 over n to the power of 1 over 2, which is the same as the square root of x to the 1 over n. So we're just using that property of limit to distribute underneath the square root. So once we have that, what exactly do we have? Well, x to the 1 over n, that's just the limit of am. So that's just equal to the square root of the limit of an. And then what we have here is an equation that contains our limit value L. So we have that L is equal to the square root of L, which means that L is equal to 0, or L is equal to 1. But we already know that the sequence is bounded above by 1, which means the limit is greater than or equal to 1. That means 0 is not possible here. So that means the limit, in this case, is equal to 1, which completes the proof. And we prove that just by using or choosing a subsequence of that, premised on the fact that we already knew that the sequence converged by the monotone convergence theorem. The next theorem that we're going to take a look at comes as a direct result of the previous theorem. Keep in mind the previous theorem said that if we have a convergent sequence, then any subsequence of it is also going to converge to the same exact limit. So this theorem looks about it in the contrapositive manner. That is, if we have a sequence and we find two subsequences that converge to different values, that means the overarching sequence is going to diverge. So this little theorem is actually useful for proving divergency of sequences. So let's look at a couple examples. So let's look at the first sequence am, which is going to be again minus 1 to the power of n, where n is in the set of natural numbers. And we already know what the sequence is going to look like, starting with minus 1, 1, minus 1, and so on. So how to prove that this sequence diverges? So we're going to be choosing two subsequences that both converge to different limits. So choose Bn to be equal to A2n, where n is in the set of natural numbers. So by definition, that's going to be minus 1 to the 2n, where n is in the set of naturals, which is going to be equal to 1, 1, 1, 1, and so on. And using the definition of limits of sequences, you should be able to verify that the limit of Bn will be equal to 1. So if our goal is to find or prove that the sequence AN diverges, we need to find another sequence, let's call it Cn, that is going to converge to a limit that is not positive 1. So you can easily choose A, 2n minus 1, so the odd values starting at 1 and so on. So it's going to be equal to minus 1 to the 2n minus 1, where n is in the set of naturals. So that's going to be equal to minus 1, minus 1, minus 1. So that's just another constant sequence. So it's very easy to see that that's going to be equal to, in terms of its limit, minus 1. Right? So what do we have here? So we have that Bn and Cn are both subsequences. So this is both subsequences of AM with different limits, because 1 and minus 1 obviously are not equal to each other, and therefore by this second theorem that we presented, AN diverges. Because if it does converge, then any two sequences will converge to the same limit as the sequence under investigation. Right? Let's actually look at another fun example. Let's look at AN is equal to the sequence, the sine of n pi over 4, where n is in the set of naturals. Right? So we're looking at our 45-degree rotation. So 45, 90, 135, 180, 225, 270, and so on in that sequence. Right? So again, if you know your values of sine, especially on your unit circle, then building subsequences of this is actually very, very easy, because we know that the sine of x plus 2 pi will be equal to the sine of x, and that's for all x in the set of reals, because this is a periodic function where the period of this function is 2 pi. All right, so there's several different subsequences you could build here, but I'm just going to give you, a couple of the easier ones that you could build. For example, we can choose Bn to be equal to the sine of 1 pi over 4, and then you can choose sine of 9 pi over 4, so that's just plus 2 pi in case you're curious. And then I'm going to go sine of 8k plus 1 pi over 4, right? So that's the general term of the sequence. So what I'm looking at is just the quad 1. So these are just the quadrant 1 45-degree references, right? And if you know anything about your unit circle, then you should know that each of these is equal to the square root of 2, the square root of 2, the square root of 2, and so on. So it's very easy to see that I've just created a constant sequence, so the limit of Bn is equal to the square root of 2 over 2. So if we're trying to prove that AN diverges, all you need to do is just find a different sequence that converges to a different value that is not the square root of 2 over 2. So what you can do is you can choose Cn to be equal to, let's just rotate all of these by 45 degrees. So that would be the sine of 2 pi over 4, and then the sine of 10 pi over 4, all the way out to the sine of 8k plus 2 pi over 4, and so on. So these are all of your 90-degree angles plus 2 pi k, where k is in the set of integers, right? So we're just looking at the positive vertical x-axis, and we know that all of those values are just going to be equal to, so cosine x sine y, so the sine value is all going to be equal to 1. So we're going to have 1, 1, 1, 1, and so on. So obviously the limit of Cn will be equal to 1. And since Bn and Cn are subsequences of An with different limits, square root of 2 and 1, therefore we have that An diverges, right? So this is very, very powerful, especially if you understand the sequence you're working with, in order to justify that a sequence diverges. Just choose any two subsequences that converge to different limits, and you're practically done. Now let's define a new term for this conversation. Let's define a point AM that's an element of a real-valued sequence. So we call that point a leader point of the sequence if for all n greater than or equal to the index of investigation or interest, that value is greater than or equal to all values that follow after it. So the easiest way to sort of get an idea of what a leader point actually is to look at sort of a diagram. So here's our indexing set n, and here's the real values an that we're interested in, and let's assume that these are our sequence values. Right, so here we have A1, A2, A3, A4, A5, A6, A7, A8, A9, A10. So the question that I want to present first is, is A1 a leader point for this presented sequence? Well, if it is, then for all indices that follow after 1, that value must be greater than or equal to that value. But it appears that A2, A3, A4, and A5 are bigger than it, so A1 cannot be a leader point. Using this idea, you should be able to see that A5 is a leader point, provided that this stays decreasing after 10, right? So this right here would be the first leader point, provided that it stays decreasing. And then this next point is also a leader point. It's the second leader point, because it's greater than or equal to all values that follow after it. And this next value will be the third leader point. So the third leader point, and if it stays decreasing, then all points after that will also be leader points as well. Right? So with this idea, the next theorem actually makes a lot of sense, and it's actually not too hard to prove. So let's assume that an, from n is equal to 1 to infinity, is a real valued sequence. Then, if one of the following two things is true, then the number of leader points should be obvious. So let's assume that am is increasing. So what can you tell me about the leader points? And you might want to pause this video to sort of think about what I'm about to say. So also, if you have a decreasing sequences, what can you tell me about the leader points? So if you have an increasing sequence, then it has no leader points. And if it's a decreasing sequence, then all points are leader points. So is it possible to have no leader points? Is it possible to have one leader point? Is it possible to have infinitely many leader points? All the answers to those questions, obviously yes, and you should be able to provide examples for them. Right? Now, let's introduce a very important theorem, and it's going to be the following. And this is called the monotone subsequence theorem, or MST for short. And it says the following. So if an, where n ranges from 1 to infinity, is any real valued sequence, so it could be convergent, divergent, bounded, unbounded, increasing, monotonic, strictly monotonic, and so on, then there always exists a monotonic subsequence. There always exists a monotonic subsequence for every sequence, even if it diverges, right? And that's a very, very subtle and sometimes not obvious thing, right? So this guarantees the existence of a monotonic subsequence. Now, you might not be able to quickly find it or explicitly specify what that is, but this theorem in some sense guarantees the existence of one. Before we get into the proof of this very interesting MST theorem, let's actually do a quick numerical example to sort of illustrate what this means. So if this theorem is true, what do we get? So let's consider the sequence sine of n, where n is in the set of natural numbers. So the question I propose to you is the following. Does an have a monotonic subsequence? Does it have one? Even if you have never analyzed this sequence, it's indeed a sequence. So does it have a monotonic subsequence? According to the monotone subsequence theorem, the answer is yes. Then the fun part becomes, can you find it? Yes or no? That's another investigation. And sometimes it can be very complicated depending on the sequence. So let's actually look at this. So if you find the value of sine of 1, and let's assume that n is in radians, of course, one can find that this is approximately equal to 0.84. So that's the very first term of your sequence. And then the next point you would have to find, what about sine of 2? Is that bigger than sine of 1? So that's 0.909, right? So okay, so it seems that we've started building a monotonically increasing sequence. That's pretty good. Now if you try sine of 3, sine of 4, sine of 5, sine of 6, and sine of 7, you won't get a value that's bigger than sine of 2. But once you hit sine of 8, you'll have that's approximately equal to 0.989, and so on. And you can try sine of 9, 10, 11, 12, and 13. Those will not work. And the next value that would be greater than sine of 8 would be approximately equal to 0.9906. And you can try 15, 16, 17, 18, 19, 20, and so on. And you will not get another value bigger than sine of 14 until you hit the sine of 33, which will be approximately equal to 0.99991, and so on. So here's a little numerical question for you. Who is the next smallest natural number bigger than 33 whose sine value is larger than the sine of 33? Right? So if we look at this and we look at b of n, which is equal to a1, a2, a8, a14, a33, and so on, this is a monotonically increasing subsequence of this sequence sine of n, where n ranges from 1 to infinity. And that's pretty neat. Obviously, some number theory people might try and see if they can find a pattern for this 1, 2, 8, 14, 33 sequence. And once you find that next number after 33, maybe you might see a cute little pattern, right? But this theorem guarantees the existence. It doesn't mean you can explicitly state it in terms of functions that you know, but it does guarantee its existence. So let's see if we can give a formal proof for the monotone subsequence theorem, which is actually very, very important, has several different applications. So it says that regardless of the sequence we choose, there always exists a monotonic subsequence. So we have to construct one in order to justify that this is indeed the case. So we can't pick a monotonic sequence, we can't pick a bounded sequence, we have to pick an arbitrary sequence, right? So we practically have nothing to use, generally speaking, right? So we have to let an be an arbitrary sequence in R, right? So this could be unbounded, it could be increasing, decreasing, it could be oscillatory, like -1 to the n. It could literally be anything. So what is one thing that must be the case for this, right? So a case-by-case analysis, maybe if we can partition this sequence into like finite versus infinite, countable versus uncountable, and so on, maybe we can get somewhere there, right? So one way you can go about this is analyzing it in the following manner. So A of n either has finitely many leader points. It either has finitely many leader points, or it has infinitely many leader points, right? And that partitions the set of all sequences, right? And keep in mind, 0 leader points would be classified under the finitely many, okay? So let's see if we can analyze these two cases. So case 1, let's actually do the infinitely many case first. So let's suppose that an has infinitely many leader points, right? And let's list them out. So let's list them as am1, am2, so am1, am2, am3, and so on. And let's list them in the order for which they're presented, right? So keep in mind, if am1 is a leader point, it must be greater than all of the ones that come after it, right? So it must be greater than the next leader point, am2, and it must be greater than am3, and so on, right? So here, M1 must be less than or equal to M2, must be less than or equal to M3, and less than or equal to, and so on. So those are all of our leader points, right? But what type of sequence have we built, right? So AM1 is greater than AM2 is greater than AM3. That's what type of sequence? Well, so AMK, where K ranges from 1 to infinity, is a decreasing. Now, we don't really need a decreasing sequence, but it is monotonic, right? And in particular, it's a subsequence of AM, right? And that completes the proof, at least for the case 1 scenario, right? So if it has infinitely many leader points, we can list them in this order, and that generates a decreasing monotonic subsequence of AM. So that's actually quick to construct. So let's look at case 2. Let's suppose that AN has finitely many leader points, and we're going to define them in a set, a finite set moreover. We're going to define them to be in the set L, the set of leader points, AM1, AM2, all the way down to AM capital M, right? Where the cardinality of L is equal to capital M in the set of natural numbers, right? Now, if we have, if the special case, if the cardinality of L is equal to 0, then that means we have an increasing sequence, right? That's a fun little proof in case you want to investigate it, right? But if we have 0 increasing sequences, so I guess you could call that case 3, then it's actually pretty trivial to build, right? So what is so special about L? Well, L is a bunch of real numbers. That much is obvious, right? So we have L as a subset of real numbers, so we have a finite subset, in particular finite bounded subset of R, right? And if it's a finite bounded subset of R, then that means that the supremum of L and R exists, right? And that's obviously the completeness accent that I'm quoting there, right? So this number is just a real number. So that means also that there exists a n in the set of natural numbers such that the supremum, which is just a real number, is less than that natural number, because we know that the natural numbers are not bounded above in the set of real numbers. So that's just the Archimedean principle that I'm quoting, right? So if that is the case, so since n is bigger than the supremum of our leader points, that means that n is greater than ANK, and that's going to be true for all k in the set 1, 2, 3, up to capital M, right? So if that is the case, that means that n is not a leader point for that sequence. So if that is the case, well, what can we do with it? So now we're going to build our sequence. So we're going to define n1 to be equal to capital M, and we're going to define nj plus 1 to be equal to the minimum of all indices k bigger than nj, where j is an element of the set of natural numbers, such that ak is greater than amj. So what exactly is this set? So let's actually take a moment and look at it. So it's the minimum, because keep in mind nj plus 1 is just an index of a subsequence. So it's the minimum index that gives us the next largest element of L, right? So if that is the case, then what do we have? So that means that this sequence, AN1, AN2, AN3, so these indices, N1, N2, N3, are given us values such that AN, those points, and keep in mind these are coming from the set of leader points, this is an increasing, also finite, monotone subsequence of AN. And that's all we need, and that completes the proof of the monotone subsequence theorem. right? And that's actually pretty good, and we've already sort of done a numerical example to illustrate that. But there's another theorem that is sort of a bit more broad, but practically equivalent to the monotone subsequence theorem, and it has a special name. It's called the Bolzano-Weierstrass theorem, so the BW theorem. And it says that every bounded subsequence of real numbers, every bounded subsequence of the set of real numbers has a convergent subsequence. So even if the bounded subsequence or subset, or that should say every bounded sequence of R, even if that sequence is divergent, it always have a subsequence that does converge, right? So how would we prove the Bolzano-Weierstrass theorem? So again, every bounded sequence of R, so that's our assumption. So we're going to let an from n is equal to 1 to infinity be a bounded sequence in R, right? So if it's a bounded sequence in R, that means there exists an m in the set of real numbers that's positive, such that the absolute value of an is less than or equal to m for all n in the set of naturals, right? Also, in parallel, since this is a sequence in R, we don't necessarily need bounded for this next statement. By the monotone subsequence theorem, there exists a subsequence a n k, where k ranges from 1 to infinity, that is monotonic, right? So we have the definition of bounded here, and we have the consequence of the monotone subsequence theorem here, right? So if that is the case, so since our whole sequence is bounded above, any subsequence will also be bounded above by m, right? So that means the absolute value of a and k, our subsequence, will also be less than or equal to m, and that's going to be true for all k in the set of natural numbers. So our subsequence, which is our goal, is bounded above, right? And it's also monotonic, right? So by the monotone convergence theorem, since a and k is bounded both above and below, and it's monotonic, I don't really care if it's monotonically increasing or monotonically increasing. It's one of them, right? So if it's monotonically increasing, since it's bounded above, or if it's monotonically decreasing and it's bounded below, in either of those cases by the monotone convergence theorem, that means this subsequence converges, right? And that completes the proof for the Bolzano-Weierstrass theorem, right? So subsequences are very, very useful for a variety of purposes, and I've illustrated a few things here, but we'll introduce a few more applications later on. So I hope you enjoyed this video, and I'll see you in the next video where we continue our exploration of sequences. Take care.